Today we are going to do this exam. It is a May-June 2024 and variant 51. Okay. So the first question goes as figure 1.1 shows a small solid metal cylinder of mass M, length L, and diameter D. So we know the dimensions of this cylinder, and it has a mass of M. The cylinder is heated to a uniform temperature. The cylinder is then removed from the heat source, and the cylinder is wrapped in an insulating material. So we are heating this cylinder in an oven or something similar. Then as it reaches some temperature, we take it out. We put it on an insulating material. Okay? Are you following?
Yes, I am.
Okay, good. The temperature of the room is TR. So TR is the room temperature. At time T, after the cylinder starts to cool, the surface temperature of the cylinder is Tc. It is suggested that Tc is related to T by the relation so and so. Where A is the total surface area of the cylinder, C is the specific heat capacity of the metal, U and Z are constant. Okay, so can you tell me how we are going to proceed with this experiment? What they are doing in this experiment? So try to read this again. Read this again. Can you read them, Dim?
Okay. The cylinder is heated to a uniform temperature. The
Yeah.
cylinder is then removed from the heat source, and the cylinder is wrapped in an insulating material.
Yes.
The temperature of the room is TR. At time T, after the cylinder starts to cool, the surface temperature of the cylinder is Tc.
Okay. So how do you think they are going to proceed with this experiment? If you are asked in a lab to carry out this experiment, what will you do?
I will change the temperature.
Sorry?
I will change the temperature every time.
You are going to change the temperature? Which temperature?
Uh, for heating the cylinder.
Actually, not accurate, because read again. The temperature of the room is TR. Then this is constant, right?
Yes.
Okay. We are carrying the temperature in a room, then we always keep the room temperature constant. At time T, after the cylinder starts to cool. Okay, this is important. At time T, after the cylinder starts to cool, the surface temperature of the cylinder is Tc.
Okay. I can wrap it with different insulating material.
No, he didn't tell us that. Look at this statement, team. This one. What does it say?
At time T, after the cylinder starts to cool, the
Yeah.
surface temperature of the cylinder is Tc.
What does that mean?
They will measure the time of the surface to cool.
Sorry?
They will measure the time
Okay.
for the surface temperature of the cylinder to cool.
Yes. So we heated the cylinder in an oven, right? It
Yes.
reached some temperature. Say it reached 80 degrees centigrade, okay? Okay, we took it out of
Okay.
the oven. Wrap an insulating material around it, right?
Yes.
Okay. Then what is going to happen to this piece of metal? as it sits out?
It starts to cool.
It starts to cool, right? As time goes on, it starts to cool. So what we are going to do is we are going to use a thermometer. We make it or fix it tied to the cylinder, right? And
Yes.
use our stopwatch. Okay? We use a stopwatch. Then we start our stopwatch. It starts at time 0, right?
Right.
Okay? Then we measure a temperature of the cylinder, right? Say we measure a temperature of 75 degrees when time was 0. Okay? Then
Okay.
what we are going to do next? Say after 1 minute, after 60 seconds, what do you expect the temperature to be? The same, higher, lower, what?
Lower.
Lower, right? Then we measure again after 2 minutes, for example. We are going to get a temperature TC. And we continue to do that for some time. For example, for half an hour. Okay?
Okay.
Okay. So we are going to get temperature TC as it is cooling down for half an hour at a constant interval of 1 minute. For example, it could be every 5 minutes, every 2 minutes, as we decide. The problem here or the question here doesn't need to know this kind of details, okay?
Okay.
Can you now imagine how this experiment goes?
Yes.
Okay. Now, as we always do, what is the first thing to do?
We write what each letter stands for.
Yes, we start defining the different parameters involved in this experiment. So, you have TC, right? And we have T. Is that right?
Yes.
We have, what else?
D.
Sorry, V. Is it V?
No, D.
D. Okay. Small d, right? What else?
And length.
A length, L. Okay. But are these parameters? Let me check again. Where is the equation? So Dean, you say D and L, right?
Yes.
But are they in the equation?
No.
No, those are not, yes, they are parameters in our problem. But what values we write are the values in the equation. Okay?
Okay.
So what else? T is there. TC is there. What else?
Okay. Okay, Mr. Can you go up to so I can see the
Oh,
equation?
sorry. You don't see it. Okay, sorry. Here it is.
Z E.
Z. This E?
Yeah. No. No.
No, this is an exponential, right?
Yes.
Okay, this is another.
U.
Sorry?
U.
U.
A.
A, capital A.
T.
We said, okay, T.
T.
Capital T.
M.
M, capital M, right? Or small m. What else?
C.
C, right? So Z, U, A, T, C, M, and we have TR, right?
Yes.
Okay. Now, can you decide from here which one is going to be the independent and which one is the independent?
It is. Okay. Mr. Okay. The dependent is the TC,
Dependent is TC, right?
and independent is T.
The time, right?
Yes.
Yes, okay, right. So we have time, dependent, independent. This one is the dependent. Why did we decide for that? Because time, it goes so we can control or we can easily measure, right? We can measure each interval, right?
Yes.
Independent, it is the temperature of something we need to measure. Then we have TC, TR, room temperature, constant, right? A, surface area, constant. We have to measure, right? C, specific heat, also constant. All these we need to measure, right?
Yes.
What about U and Z?
They are constant.
But how are they different from those?
Different from which?
From these constants? How are they different?
We don't use them in the experiment.
No. The difference is that those values we are going to calculate from the gradient and the intercept, right?
Yes.
Those ones we are going to measure when we are doing the experiment. Those ones we are going to calculate later on after we get our gradient and after we get our intercept, right?
Yes.
Okay, good. Okay, so now let us make small sketches here and there to show, for example, this is an oven. Oven to heat the cylinder. Okay? So we have an oven. We have our cylinder. So can you tell me which instruments are we going to use, Dean, for this experiment?
Okay, so room temperature, we can use the thermometer.
Okay, good.
Surface area, we can use the caliper vernier to measure the diameter, and we can use the formula pi r square.
Okay.
Specific heat capacity, it is mc delta t. So we
need
should
to carry
measure
some
the mass.
experiment to calculate C, right?
What?
We are going to carry another experiment to calculate C, right?
Yes.
Okay, good. What else do we need?
We need the formula of a straight line to calculate
No,
the constant.
instruments for now.
Ah, okay.
Okay. So we need a kind of a caliper to calculate the dimensions, right? We need a thermometer to calculate the temperature. What else? By the way, we missed a parameter over here. It is a mass, right?
Yes.
Okay, we have the mass. So what we are going to do for the mass?
Using a balance.
Sorry, a balance. Okay, what else?
For T, we can use the stopwatch.
And we need the stopwatch to measure time. Okay, I think we are done almost. So let me draw. This is the thermometer, right? Okay, this is thermometer.
Okay.
And we wrap it. I don't know how we show the wrapping, but maybe we can do it something like this. And we say insulating material. Okay. Are we good?
Yes.
Okay. Now, let us do that. We start by telling how we are going to carry out the experiment, right? Or what values we are going to measure. For example, the first one, we can say use a digital scale balance to measure the mass M of the cylinder. 2, we need to calculate the area. By the way, Dean, this is the cylinder, right?
Yes.
And what is A?
Surface area.
Surface area of the whole cylinder, right?
Yes.
Surface area of the whole cylinder. So how many surfaces this cylinder has?
2.
Is it only 2? Let us count. So the top is 1, right?
Yes.
Okay. The bottom is 2, right?
Right.
What about the sides?
2. Also 2.
No, it is a third surface, right? Can you imagine the cylinder? It got a bottom cylinder, a surface, a bottom one, and the sides of the cylinder, right?
Yes.
Okay, so we need to calculate the 3 surfaces, right?
Yes.
Okay, so what do we need? We have D, we are going to use a caliper to measure D, right? So it is D, diameter over here. What is the surface area of this top surface?
The formula
Yes,
by R square.
pi r squared, but we are measuring D, right?
So y over 4d square.
Pi d squared over 4, right? And we're going to multiply by 2 because we have the top and bottom, they are equal, right?
Yes.
What about the surface area of this, the outside surface?
We can use a meter ruler
To measure what?
to measure the third part.
Yes, but the ruler is only going to give us the height or the length, doesn't give us the surface area. How we are going to calculate this surface area? You didn't have it in your math course?
I'm not taking math.
I think, but this was on the O level, I think, the IG.
So it is pi RL.
Pi RL, yes. But again, we are not doing R, right? Pi
D
D,
square
right?
over 4.
L divide 2. You say pi RL, right? This is right. What is R?
D.
D over 2, right?
Yes.
Okay. Then the total surface area is equal pi D square over 4 plus pi DL over 2. Okay?
Okay.
Okay,
The
good.
first one multiply 2.
Sorry?
Pi D
Oh,
square over 4 multiply
sorry.
2.
This one is 2 pi R. 2 pi R times L. Okay, it is pi DL. Sorry. We don't have a half here. Okay?
Okay, and the first one we should multiply it by 2, right?
Yes, we should multiply by 2. So this is the total surface area, okay?
Okay.
Okay, good. Now, we are going to tell him, measure the length L of the cylinder using a meter ruler. 3, measure the diameter D of the cylinder using a vernier caliper. 4, calculate the total surface area A as pi D square, 2 pi D square over 4 plus pi DL. Okay? Are we good, Dean?
Yes.
Okay. Now we say that repeat the readings
Twice and find the average.
twice and use the average values for further investigation. Okay? Now we come to the heat capacity part. Do you know how to measure the heat capacity of an object? Have you done it
It
in
is,
your
it is
thermodynamics part?
MC delta T.
Sorry?
MC delta T.
MC delta T, right?
Yes.
But the experiment that you can carry to calculate the measurement,
Yes, I know it.
how can you do?
Oh no, I don't know it.
Okay, then this is how you do it. There is an electric method. They call it the electric method. Okay, so what do? We have a beaker. Or they call it the calorimeter. Do you know a calorimeter? Have you heard about it before?
No.
Okay, calorimeter is a metal, okay, a metal cylinder, okay, made out of copper or aluminum. It is typically copper. Okay, it is a cylinder made of copper. Okay.
Okay.
Okay, and it got a heating element. It got a heating element like this. Okay, this is a heating element. Like a coil, if I pass current through it, it will start heating up. Okay,
Okay.
then we have a battery or a voltage source, whatsoever, power source, power source. We have an ammeter. Okay, and we have a voltmeter. Let me draw it in a better way. This is our calorimeter. This is our heating element. This is an ammeter. It's our power source. Okay, and over here we have a voltmeter. Okay,
Okay.
and we fill this one with water. We fill the calorimeter with water, and we put inside of it the object that we would like to calculate the specific heat for it. Okay, are you following?
Okay.
And we
Yes.
also have a thermometer. We have a thermometer, right?
Yes.
Okay. So the whole idea in this experiment, you don't need to write details, right? We don't need to write details, but we just need to show him that we know how to proceed. Okay.
Okay.
Okay. So, but I'm giving you more details. So in case that you get something similar, you can just recreate it. Okay.
Okay.
What we do is we start heating up using this heating element for a time t. For example, for half an hour. We let the current pass for half an hour. We know I, the current, we know V. Do you know how much energy is dissipated by the heating element if we have a voltage V, a current I, and a time t?
Yes.
How do you do that?
VA over T.
No. VI times delta T, the time. It is VI times delta T. This is the amount of energy given out by the heating element to the water and the object. Okay.
Okay.
Then this one is going to be mass of water, specific heat of water, delta T of the water plus mass of the object, specific heat of the object, and the temperature change in the object, right?
Yes.
If we know V, VI, we know delta T, those are all fixed. We know the mass of the water used, the heat capacity of the water used, the change in temperature, the mass of the object, the temperature change of the object. Then we know everything. Then we calculate the specific heat. Okay? We're not
Okay.
going to write all these details, but I'm just giving for you to have an idea. So use an electric method to calculate or measure the heat capacity of the cylinder. Okay, this is all what we need to tell him. Okay, Dean?
Okay.
Use an electric method to measure the heat capacity of the cylinder. What you can do, you can just draw this diagram and all is fine. Okay?
Okay.
Now, we are almost done with everything. Now we have 7, using an oven, heat the cylinder to a temperature no, we don't need to say to a temperature. Oven, heat the cylinder. Okay. 7, 8, fix a thermometer to the surface of the cylinder and wrap it in an insulating material as shown above. Okay, we are going to fix a thermometer to the surface of the cylinder, and then we are going to wrap it in an insulating material. 9. Using a thermometer, measure the temperature, the room temperature, PR. Okay. Make sure to keep the room temperature constant throughout the whole experiment, right? Are you
Yes.
following him?
Yes, I am.
Okay, good. Then, using a stop watch, read the temperature of the cylinder as it cools down. Okay. Measure, take measurement. at constant time intervals for example, each minute for a total time of 30 minutes. Okay?
Okay.
There is nothing fixed about 1 minute and 30 minutes. It could be every 2 minutes and for 15 minutes, okay? For a total time of 15 minutes, okay? So there is nothing fixed.
Okay.
But what we need to emphasize for him, we are going to take measurement of temperature at constant time intervals, okay? For a certain period of time. This is what we need to tell him. 11, tabulate the readings in the table below. Okay, Dean. Think our time is running out. We come back in 10 minutes, but before that, can you take a screenshot for this equation? Can you make a screenshot? Can you make a screenshot for this equation, Dean?
Yes, I did.
Okay. Okay. What I need for you to do for me in this 10 minutes to tell me, okay, how we are going to change this equation into that of a straight line. Okay. And what parameters do I need to have in my table? Okay.
Okay.
Okay. So we have everything. I would like you to see or show me how we are going to change it into that of a straight line. Remember, y is equal mx plus c, right?
Yes.
Okay. And if it is exponential, what do you think we need to do?
Multiply ln.
Sorry? We don't say multiply. You say apply.
Apply.
Apply, okay? We don't multiply by the lim function or the log function. We apply the lim function to both sides, okay? So do
Okay.
that and tell me what do we need to put in our table to plot. Okay?
Okay.
Okay, then I'm going to end it up here and see you in 10 minutes.
Okay.
So this is what you send me, right? Can you
Yes.
see? Is ln TC minus ZUA over MCT plus ln TR. Is that right?
Yes.
Okay, but this is not exact. Let us see why. What are we going to do? Apply ln to both sides, right?
Yes.
Okay. Then we have this side and we have that side. Then it is ln TC minus T over TR, right?
Yes.
Okay, is equal ln Z, okay, E minus UA T over MC, right?
Right.
Okay. Now, let us have a look at this side. It is ln Z times the exponential, right?
Yes.
Okay. Those are two functions multiplied together. Ln A times B. Okay?
Okay.
Then what is ln A times B?
Ln A plus ln B.
A plus ln B, right? Then two functions
Yes.
multiplied together, then it is going to be ln Z plus ln E minus UA T over MC. Is it?
Yes.
Then we are going to get this one down there, down here. Is equal ln Z minus U A T divide M C and ln E. Right?
Yes.
But what is ln E?
It is 1.
1, right? So we just remove it. Okay. For ln A plus B, ln A plus B is not equal to ln A plus ln B. It is not. So we cannot actually separate TC from TR in here. Then we are going to leave it as it is.
But Mister, I separated them before I applied the ln.
Okay, it is going to be even worse. I'm going to show you why you cannot do that. Okay? So let us see what you were saying. You were saying that you said TC is equal Z E minus UA T divide MC, right? Plus TR. Is this what you are saying?
No, I removed the E
How did you remove it?
because ln and E equal 1.
Yes, but you cannot, when we do it as a whole. We take the whole ln function. We don't remove it here, and then it doesn't work like this. Okay? The first step is to take the ln function of both sides. Like this. We take the ln function for both sides. Okay, Dean?
Okay.
We don't say that we are taking this ln function, and after we are done, then we take the ln function on the other side. It doesn't work that way. So maybe you did say like TC minus TR is equal ln, I don't know, ZE minus UAT over MC, like this.
I did it wrong,
Yes.
but
Okay.
I got it now.
Yes. So what we do, we take the ln function. We have TC minus TR is equal ZE minus UA T over MC. Okay? When we do the ln function or the log function, we do it for both sides at the same time. So it is ln TC minus TR. This is one side. Equal ln of both of them. Ln for both sides at the same time. Here we cannot separate TC from TR because this cannot be separated. So we keep it as it is. What we can further do is separate this into ln Z plus ln E minus UA T over MC. This can be further simplified. Okay? Is that clear for you, Dean?
Yes, it is.
Okay. So now we come back to our table. We have to write the equation over here. We say it ln TC minus TR minus equal minus mu A over MC times T plus ln Z, right?
Yes.
This is what we have. Then from here, we are going to decide what goes into the table. The first thing that needs to go into the table, what do you think, Dean?
It is independent.
Independent. Which one?
T.
T. What are the units for T?
Second.
Second. What else?
Then the dependent, which is TC.
TC. Units?
Also second.
No. TC is the temperature.
Degree Celsius.
Degree centigrades. Okay. What else do we need here in this table to make it be able to draw a line?
Ln TC minus TR.
Okay, good. Remember, what is TR?
Room temperature.
And we have measured it once. Okay, and it is fixed through the whole experiment, right?
Right.
So if the temperature here is 50 degrees and room temperature is 25, then it is going to be ln 50 minus 25, right?
Right.
Okay, good. Do we need to put the units over here?
No, it doesn't have a unit.
Doesn't have a unit, okay? Now we tell him, make a graph plot of T x-axis and ln TC minus TR on the y-axis. 13, calculate the gradient equal. What is the gradient going to be?
Minus UA over MC.
MC. Good. 14, calculate the intercept. What is the intercept going to look equal?
Ln Z.
Ln Z. Okay. So what is U?
MC multiply gradient. Minus MC multiply gradient over A.
Good. What about Z?
Intercept over ln.
No. Remember, I sent you the rules for the ln.
Yes.
Remember this, Dean. We have, for example, Z equal what should I write here? E to the power.
E to the power of n temperature.
Okay. What if I take ln Z? It's going to look like this, right?
Yes.
So we do the opposite. We do the opposite. We remove the ln from here, but what is in front, we take it to the power of the E. Okay?
Okay.
Revise this rule, okay?
Okay.
In your mind. Okay. Now I think we are done with almost everything except the last thing with the precaution and what is he saying the last thing? Safety precaution to be taken.
Wear gloves.
Sorry?
We can say wear gloves when using the oven.
Yes, we can say that. Or just say take caution when handling the oven and the hot cylinder, right? You can say wear use gloves, whatsoever. I mean, nothing. As long as we tell him that he should be careful with when handling the hot elements. Okay?
Okay.
Are we good?
Yes.
You have questions?
No.
Okay. So let us proceed to question number 2. It tells us a student investigates the sound from a horn attached to a car, as shown. So we got a horn in a car, and we use an instrument to measure the frequency. Okay? A microphone is placed at the side of the road and connected to a frequency meter. Frequency meter is used to measure frequencies. The car travels towards the microphone. The frequency F of the sound detected by the microphone is read from the frequency meter. Okay? The speed of the car is measured by 2 speed detectors. The 2 measurements of speed are V1 and V2. So he's measuring the speed twice, okay? The average speed V of the car is determined, V1 plus V2. It is suggested that F and V are related by this equation. So the frequency is equal Fs K divide K minus V. Okay?
Okay.
Okay. Where Fs is the frequency of the sound emitted by the horn and K is a constant. So we know Fs is a frequency of the horn and K is a constant. He's telling us a graph is plotted of 1 over F on the y-axis and V on the x-axis, right?
Yes.
Okay, good. So can we tell which one is the dependent, which one is the independent?
V is the independent and F is the dependent.
Good. So how we are going to handle this equation to look like that of a straight line? What do you think?
First, we'll write y equal mx plus c.
Okay. What else do we need to do?
Make F in one side and V in other side.
But we already have F on one side and V on the other side.
So say 1 over F.
1 over F equal
Fx
sorry.
Fsk
Mm-hmm.
over K minus V.
Mm-hmm. Remember, Dean, always remember what you do to the left side, you do to the right side. Can you hear me, Dean?
Yes, I can.
What we do on the right side, we have to do the same to the left side, right? So what did we do to the left side?
We make it 1 over F.
We make the inverse. So what should we do to the right side?
We should make it K minus V over FSK.
Yes. Now, can we separate? Can we further simplify this equation to look more like one of a straight line?
Yes. I can say K over FSK
Yes.
minus V.
Okay. Only minus V? Remember, this one, it divides both values. It divides the K and it divides the V. So for
over
A
FSK.
plus B, divide C. C doesn't only apply to the A, right? It goes to the A and goes to the B. Right?
Yes.
We further simplify. Then we have 1 over F is equal minus V divide FSK plus K over K goes away, 1 over Fs. Okay?
Okay.
Are we good? Let me just write it better. So I say 1 over Fs, 1 over F is equal K minus V divide Fs K. Okay, 1 over F is equal minus V divide Fs K plus K divide Fs K. Those goes away. So what is the gradient?
Negative 1 over FSK.
Okay. What is the intercept?
1 over Fs.
Okay. Now we have the values of V1 and V2 and F given in the table. Okay? So we have V1 and V2. Calculate and record values of V and 1 over F includes the absolute uncertainties in V, right? So how we are going to calculate V?
We will find the average.
We're going to find the average, right?
Yes.
Okay. So it is 3.9 plus 3.1 divide 2. 3.1, right?
Yes.
No, it cannot be.
3.5.
3.1 plus 3.9. Yes, 3.5. This cannot be. Yes, 3.5. What about the absolute uncertainty in this one? How to calculate?
It is the maximum minus the average.
Maximum minus the average, okay? So it is 3.9 minus, what is the average?
3.5.
3.5. 0.4. Okay? Can you do yourself? The remaining?
Yes.
Okay. Can we do them quickly?
5. It is 6.3.
6.3 and the absolute?
0.4.
0.4, right. What else?
It is 8.7.
Yes.
So it's 9.2 minus 8.7, right?
Why? 8.7 minus?
9.2.
Yes.
It is 0.5.
Yes.
Okay, mister, I think the second one is wrong.
Second one, which one?
Its absolute uncertainty is, no, it is correct.
Yes, it's correct.
So 11.9 plus 10.9 over 2 is 11.4.
Yes.
11.9 minus 11.4, it is 0.3.
No.
Okay. 0.5.
That's 0.5.
14.5 plus 13.3 over 2, it is 13.9.
Yes.
13.9 minus 14.5, it is 0.6.
Yes.
$16.2.
Yes.
0.6.
0.6. Okay, good. Now, just a question. Do you know what this phenomenon, can you notice something as the speed increases, Dean? Can you have a look at as the velocity when it was 3.5? The frequency measured by the frequency meter was what?
894.2.
Okay. As it goes, as the velocity increases, what is happening to the frequency?
It also increases.
Okay. Do you know what is this physical phenomena called? I think you have gone through it in your physics course.
Yes, we did.
What was it? Do you remember what it is called?
No, I don't.
It is a Doppler effect.
Yes.
Okay. This is the Doppler effect. Okay. And they always give us this example of a police car siren, right?
Yes.
As we are standing and it is approaching us, we could always hear that the frequency of the siren is a little bit changing. Okay? So this is the Doppler effect. Okay. Now we need to calculate 1 over f. Can you do that, Dean?
Yes.
Okay. What is the first one?
1.11 1.12.
1.12. Let me show you. Now, what do we have? 894.2. I got the inverse. It says 1.1183 times 10 to the power minus 3, right?
Right.
Did you get that?
Yes.
Now, how many significance figures should we keep?
Either 4 or 5.
Either 4 or 5. I'm going to go for 5. Okay? Then it is going to be what, Dean?
1.1183.
And we have 10 to the power minus 3, right?
Yes.
Should I write it here?
I don't think you need because it is already written.
Sorry?
I don't think you need to write it down because it is already written.
Yes, yes. You don't have to write it here because he already did it for me over here. So I know that everything in this column is multiplied by 10 to the power minus 3. Okay?
Okay.
So you see how we proceed?
Yes.
Okay. What is the next value?
It is 1.1096.
Okay, good.
The next one, it is 1.1013.
Yes.
It is 1.0919.
Good.
It is 1.0827.
Yes.
It is 1.078.
Hmm?
No, 1.0739.
Yes. Yes. Okay, good. Okay. So the next step is we start doing our graph plot, right?
Yes.
So we have on the x-axis, we are going to have the velocity, right? On the y-axis, we are going to have 1 over f dim, right? Is that right, Dean?
Yes, it is.
Okay. So what do we have over here? The scale?
It is 2.
2. Right? And what about here?
It is 0.005.
0.005. Okay, good. Now, for this time, remember or notice that the error bars are going to be on what? On the y-axis or on the x-axis?
It will be on the x-axis.
In the x-axis, exactly. Okay, so let us do the first one, 3.5.
It is 2.5 steps from 3.
2.5 steps from 3. Yes, around here, right?
Yes.
Okay, and we have 1.1183. Where is it? It is around here, right? And this is square. Right, Dean?
Yes, it is six steps from
So you did the calculation.
1.115. Yes.
How many steps?
It is 0.66, so 6 steps.
6 steps. 1, 2, 3, 4, 5, 6. Is it over here?
Yes, it is.
Okay. What about the error bars?
Um, was it 0.4? Can I see the graph? Can I see the table?
Yes, 0.4.
So it is 0.4 divide 2, which is 0.2. So 2 steps to the right and 2 steps to the left.
2 steps to the right and 2 steps to the left. Okay. So it is 1, 2. 1, 2, over here. Over here, right? Is it right?
Yes.
What else do we need to do?
Draw a straight line that passes through the X.
Okay, good. 6.3. So what is
It is 6.5 steps from 5.
6.5 steps from 5? Yes. This is 0.6, and we have 3. Sorry, 6.2, 6.3. Yes. A little bit away from. Okay. And where is 1.1096?
It is 3 steps from, no, 1 second. It is 2 steps from 1.095.
Exactly. Here, right? 2 steps, and it is here, right?
Yes.
Right. How many steps to the left and to the right?
2 steps.
2 steps. Okay, good. 8.7.
It is 8.5 steps from 7.
8.5 steps from 7, right? And where it is going to be 1.1, 1. Oh, no, Dean. This is 1.1096. So it is not here. It is not here, Dean. This one.
Okay.
It is 1.1096. Right? So it is should be
Yes.
around here. Right? So it is going to
Yes.
be
9 steps from 1.105.
9 steps. Yes. 9 around here, right?
Yes.
Okay. And then we have 2. We have 2. And we draw the line. Okay, be careful. What else? 8.7 and 1.1013.
8.7, it is 8.5 steps from 7.
Okay. This is 7. We are going to count 8. But where is it on the y-axis? Where do you think?
So which one?
This one. 1.103. 013. Okay, good. So I took the time to make the remaining points. Did you have a look at them?
Yes.
Okay. Do you have something difficult about plotting them?
No.
Okay. So as usual, we do exactly the same. If we can do the counting, okay. If not, we can do the math, right? Is that
Right.
okay? Good. Now we have to make how many lines?
2 lines.
Two lines. Which one first?
The best fit.
The best fit. How do we decide for the best fit line?
It should pass through the center of most points.
We try to make it pass through the centers of all the data points, right?
Yes.
So maybe this is a good line going through most of the centers of the data points. Okay.
Yes.
What else do we need to do? What is the next step? What should be the next step, Dean? Can you hear me, Dean?
Yes, I can.
Okay, what is the next step?
We make the worst fit line.
Yes. Okay. And maybe we can do it as a dashed line, right?
Yes, right.
To make it easier for us to differentiate. How we decide for the worst fit?
From the end of the uncertainty line to the beginning of the last uncertainty line.
So maybe something like this.
Mister, in the worst fit line, we want it to pass through most of the uncertainty line.
Yes, we try to make it go through. Can you see over here? Can you see over here where I'm trying to pass it? The edge of the uncertainty, but the one to the right, to the left, right?
Yes.
Can you see?
Yes.
Then at the end over here, I try to make it pass through the other end, the one to the right, or the other way around. It doesn't make a difference, okay?
Okay.
I try as much as I can. Okay. Then what is the next step?
We should do a gradient.
Gradient. Calculate gradient.
One for the best fit and the other for the worst fit.
Yes. So maybe I can do that. Sometimes for my personal test, I do one Dean. Okay? But let me show you how I am doing it myself. If you don't think this is a good way, then you can do what makes you more comfortable. Okay?
Okay.
So I'm using one triangle. So I come here and read this data point where it intercepts with the line of best fit. Okay, and I take this measurement for this point. It is 14.9, right?
Yes, right.
Okay,
Or 15.
sorry? Oh,
It is 15.
okay, 15. Let us say it is 15. Then what is the x-axis, the y-axis? $1.0785. Can you read it?
1.078.
85, right?
Okay.
Okay. Now, this is for the best fit. What about the worst fit?
Mr. How 1.785?
Do the counting.
Okay.
Okay. So
Yes.
76, 77, 78, right?
78.
5.
78.5. Yes.
Okay. If you don't know how to do that, if you don't like to count, do it like this. 1.075 plus 0.005, right? How many small squares? 1, 2, 3, 4, 5, 6, 7. Do it like this, Dean. 1.075 plus the scale. Oh, times 0.7, sorry. Okay, Dean?
Okay.
Okay, can you do it on your calculator? $1.075 plus 0.05 times 0.7.
1.0785.
Okay. Did you know now how to do it? If you cannot do
Yes.
counting,
Yes.
from where did I get 1.075? Because I'm starting counting from here, right?
Yes.
Okay. From where did I get this 0.005? It is the scale, right?
Right.
And how many small squares do we have?
7.
7. But I don't write 7, right? Remember, always when we get the small squares, we get them as 0 point something.
Okay.
So it is 0.7, small square lines. If you don't like to do the counting, okay?
Okay.
Now for 15, for the worst fit line, it is 15.4, right?
Right.
What is the y-axis?
It is 1.0785.
It's the same, right?
Yes.
It's making life a little bit easier. What about here? This one. What is the x-axis?
6.9.
No. This one, Dean.
4.9.
4.8. Remember, each small square is 0.2.
Okay.
Okay. What is the y-axis?
7.85.
1.0785. So it is making life easier, right?
Right.
Okay, what about here? So we again take two values, 1, 4. So what is the value over here? 4.8, right?
Yes.
What is the best fit line? It is going to be 1, 1, 1, 2, 1, 3, 1, 1, 4. 1.114. 1.114. What is the worst fit? It's going to be 4.8. 1.11, 2, 3, 1.1135, something like this. Okay?
Okay.
Okay. So if you don't like doing it with one square, then feel free to do it with 2 squares. The one that you think you can do it easier. Okay?
Okay.
Okay. So now let us go and calculate the gradients. I'm not going to use the values over here because I have already done my calculation before. Okay, Dean?
Okay.
Okay. But what we're going to do is the change in y divide the change in x. I'm just not going to use exactly the same values. So I say best fit is equal 1.1135 minus 1.075. 16 minus 5. What do I get? 0.00 39
0.934.
395. And what are the units? Ten to the power minus 3, here's minus 1. Right?
First minus 1 per meter, second minus 1.
M minus 1 second, right?
Yes.
Okay. Or you can say it is meter per second. Okay. Well, what is the worst fit? 1.116 minus 1.080 divide 15 minus 4, going to get 0.00327 times 10 to the power minus 3, hz minus 1, okay, meter s minus 1. Okay, but remember, Dean, what is the sign for this gradient?
Negative.
Negative, okay? We were not careful when we were saying which one is minus 1, right? But we know if it looks like this, then the gradient is negative, right?
Yes.
And we're just going to plug in here a minus sign. What is the gradient? Minus 3.5 times 10 to the power minus 6. Okay? Okay, Dean? Can you see the minus 6 over here?
What?
The minus 6. How did I write it? I rewrote this as how did I rewrite it?
3.95
Times 10 to the power?
minus 6.
Minus 6, okay. Okay, now we need to calculate the absolute uncertainty.
It is the worst fit minus the best fit.
I just need to recheck this calculation, Dean, okay? Very quickly. Okay, this is not 395. Three, 4, 5, okay? Okay, Dean?
Okay.
Okay. Okay, so it is 3.45. And what is this? 3.27. Right? How much do I get?
0.18.
0.18. Okay. Now we round it how to many significant figures?
To one significant figure.
1. It's going to be 0.02. Right? How many?
Mister,
Yes.
is it 3.5 or 3.45?
Okay, it is going to be 3.45, right? Right?
Right.
Okay. But now we have the absolute uncertainty. It is up to one decimal place, right?
Yes, right.
We are going to change this one to one decimal place, right? One decimal place, right?
Yes.
Okay, then it is from 3.45, it is going to be 3.5, okay?
Okay.
So always the number should have the same number of decimal places as the absolute uncertain. Okay?
Okay.
Are we good?
Yes.
Okay, good. Now we go and proceed. Determine the y-intercept of the line of best fit. Includes the absolute uncertainty in your result. So how we are going to proceed, Dean?
We should find 2 points from the best fit and 2 points from the worst fit.
1 point. It is not 2 points. 1 point. 1 point
Okay.
on the best fit and 1 point on the worst fit. Okay? Okay.
Okay.
Okay. So here are the points I'm using. Let me check what do I have. I'm using 1 point. Actually, I use 1 point for both of them, but well, 9.2, 1.099 times 10 to the power minus 3. I think I got it from here, Dean. Okay, in my graph that I did at home, okay, I get the 2 lines crossing this point.
Okay.
So they were both crossing this point. So I use it for both of them. Okay, but for you, use 2 different points. Okay. Is it okay?
Okay. Yes.
We write y is equal mx plus c. C is equal y minus mx. C is equal, now for the best fit. What is y?
1.099 times 10 to the power negative 3.
What is the gradient? We are good. We are good. Sorry. Okay, so 1.09 times 10 to the power minus 3, right?
Yes.
Okay, what is the gradient?
3.45.
3.5
Okay.
times 10 to the power minus
6.
6. And what is x?
9.2.
9.2. But we are missing something. Remember, the gradient is a minus.
Yes.
So minus and a minus?
Plus.
Plus. So if we do this mass, the mass over here, what we are going to get is 1.135 times 10 to the power minus 3. Okay?
Okay.
Okay. We do the same for
The worst fit.
the worst fit. 1.099 times 10 to the power minus 3 plus
3.3.
3.27 or 3.3 times
10
9.2
to the power negative 6.
minus 6. What do we get? 1.129 times 10 to the power minus 3. And it is here minus 1, right?
Yes.
How do we calculate the absolute uncertainty?
It is worst fit minus best fit.
Worst fit minus best fit. Okay?
Okay.
Then we do it 1.135 plus or minus 0.007 times 10 to the power minus 3. And we have here's minus 1. Right?
Yes.
Okay.
Yes.
Using your answers to determine the value of Fs and Q. Include appropriate units. So we remember that f of s is equal 1 over intercept. Right?
Yes.
So it is 1 divides the intercept is 1.135 times 10 to the power minus 3. We get 881.1 hertz. So this is 881.1 hertz. Okay?
Okay.
What about the gradient? Is equal minus 1 over K F S, right?
Okay.
Therefore, K is equal minus 1 over gradient times Fs, right?
Yes.
So it is 1. The gradient is minus 3.5, then it is 3.5, right?
Yes. Plus.
And what is what 1 over S?
1.1.
1.135 times 10 to the power minus 3. And the
This
gradient
is the intercept.
Sorry?
1 over f equals the intercept, right?
Yes. Or you can do it like this. Right?
Yes.
Okay. What you find more comfortable. 342.2. Now we need to check the units for K.
Hertz minus 1.
Sorry?
Hertz minus 1.
Not really. Let us check. So K got a units of gradient or inverse gradient. -1, right?
Yes.
And Fs -1. So what is gradient -1?
It is hertz.
It is hertz.
Meter second.
Okay. It is going to be right from here, right? The inverse of this whole thing is going
Meter minus 1 second over hertz.
over hertz -1, right?
Yeah.
Going to shift we inverse the whole thing, right?
Right.
Okay. Times, what is the units of Fs -1?
Hertz.
No. Fs in hertz. But what is the inverse of hertz?
Hertz minus 1.
So what is going to happen?
Hertz minus 1 cancel hertz minus 1.
And left meter per second -1. Sorry, meter per second. Right?
Yes.
Look how it happened here, Dean. The units, gradient, got unit of hertz -1, right? Divide meter second -1, right?
Yes.
We inverse the whole thing. So what is going to happen? Right?
Yes.
Okay, good. Let us proceed further. Determine the percentage uncertainty in K. Right? Determine the percentage uncertainty in K. So we say that K is equal what?
One over gradient multiply Fs.
Multiply 1 over Fs. Right?
Yes.
Okay, good. Do you remember when we say that delta K over K for this one? When something is function is 1 over A.
Yes.
What do we get?
Delta gradient over gradient.
Yes. Right?
Yes.
Do we know things over here? Do we know what is the error in the gradient?
Yes, we do.
We have the error in the gradient is 0.2, right?
Yes.
And what is the gradient? 3.5.
Yes.
And what is the error in Fs?
We don't know it.
We should know it from somewhere.
We can make F1 over Fs intercept.
Yes. So we say that Fs is equal 1 over intercept, right? Then delta
1
Fs,
over F, yes.
delta intercept over intercept.
Over the intercept, yes.
What is the error in the intercept? Right?
Yes, 0.007.
Yes. And what is the intercept? 1.1.
1.135.
So, and we do the math. Okay? We get approximately like 6%.
We didn't multiply it by
By
K.
100. Yes. We multiply
By
by 100, right? Are we good?
Yeah.
Okay. So this is the percentage uncertainty, right?
Yes.
So he's telling us the experiment is repeated. Determine the speed v that gives a value of so and so. So we go back to the equation. F is equal Fs K divide K minus V. We would like to make V the source of the equation. How we do that?
V equal FSK over KF.
What?
V equal FK
Fk
over
F,
FSK.
no, Dean. No. No, it's not going to go like that.
Okay, V equal FSK over
Let us do it
K
in
minus
steps.
F.
Let us do it in steps, Dean. Okay? Can we do this? Can we do this?
Yes.
Okay, good. Now, can we write it like this? Or no, better. Can we move this one up here? Can we, Dean?
Okay.
Is this okay?
Yes.
Then we shuffle V and the other side. We move it to the other side. Is it okay?
Okay. Yes.
And we just substitute. What is K?
342.2.
1 minus. What is Fs? 880.1.
Yes.
What is the value of F he is asking for?
987.8.
0.8. Then we do the math. Okay? We get something like 34.8 meter per second. Okay?
Okay.
Okay, do you have questions?
No, thank you.
Okay, then I'm going to send you 3 papers, Dean.
Okay.
I could understand that you have an iPad, right?
No, because my pen stopped working.
It's broken. Okay. Then try to print, solve as you are going to solve in an exam, right?
Yes.
And time yourself. Time yourself.
Okay.
And give
Okay.
the complete solution. Okay? And for each paper, please tell me what time did you need to use. Okay, Dean?
Okay.
You have questions?
No, thank you.
I will try to send the papers this afternoon, okay? It will be,
Okay.
you can send them me back as soon as possible.
Okay, I will.
I have time for next session to discuss. It will be
Okay.
send them by Saturday.
Okay, I will.
Okay, good.
Inshallah.
Okay, inshallah.
Yes.
Okay, good. I will send them this afternoon.
Inshallah.
Cheers.
Okay, bye. Thank you so much.
ايوه ايوه